I will show you the parts of the instrument, and then I will show you how to operate it. Now we have a big problem with the laser, so I've made it working a little bit, but it's not nearly working properly, but hopefully enough to show you how to make the system work. Okay, so flash photolysis system, we're looking at excited states, looking at triplet state usually. And to measure the triplet state, we need two light beams. We need a probe beam that shines through the sample, and then we excite the probe beam with a laser beam. The laser beam puts the sample into the excited state, and in the excited state absorbs more of the probe beam, so the light shining through the sample will decrease, and then it will relax as the sample returns to the ground state. So you will see a sharp decrease in the transient absorption and an increase again back to the ground state. We can also measure fluorescence, and for the fluorescence measurement, we just measure the fluorescence. You will see an increase in fluorescence and a decay back down again. So first of all, I will show you all the parts of the instrument. So I'll start with the probe lamp. So this is a xenon lamp. We pulse this lamp, which is what this compartment is, the pulsar unit, and the light comes here to here, gets stuck here. We have a shutter here because there's a lot of ultraviolet light in here, and if this shines in the sample all of the time, then the sample will bleach. So we have the shutter closed, and then just before the experiment we open the shutter, and the light will shine through all the way through to here, and from here it goes into a monochromator. And monochromator is a diffraction grating monochromator, and there is a grating sitting basically beneath the monitor here. So the light goes down to the back, to the monitor, onto the grating, gets split up into a spectrum, and comes to the PMT. So the PMT will measure maybe 1 nanometer, 2 nanometer bandwidth. And the output of the PMT is a voltage, which comes to the oscilloscope on this channel here. And you will see a voltage here. And then from the oscilloscope, it goes to the computer, and you will see it in the software. So this takes place over maybe 10 milliseconds, and somewhere in the space of that 10 milliseconds we fire the laser. Now the laser is sitting at the back, and it goes to here. Laser height is brought up, laser beam comes to here. So the probe beam goes like that, and the laser beam goes like that. This is called a cross beam geometry. So when the laser fires, the laser pulse is maybe 5 nanoseconds. So it's a very short pulse, very intense pulse, and you have to be careful with the laser. So that is the components. So when we start the experiment, I have a standard sample here called ruthenium bipyridine. This is just always a useful sample to have if you do not think the equipment is working properly. You can use this sample, and it will tell you whether this equipment is working. Right, so I'll put all the lids on. So, first thing I'll do is I'll switch on the laser. So, power switch here. Right. So get to this stage, then I turn this key switch, and then I press laser. Right. Now you can say open. Okay, he's waiting for this to go down to 0. Okay, so now I switch on the software. So what it does now, it goes through, it checks all the hardware that the hardware is working. The blue one you do not have, just the green one. If something becomes red, then something has failed. You have to check. Right, what I will do, I will get the chair and I will sit down so you can see above me.
এখানে কোন সুইচটা চাবিটা
One other thing I will do now, I'm ready to start. I press the green button and you hear a click. So now the laser light can come. Right. Okay, so first I need to try. So we have in your system there's two buttons that we can use. One called kinetic emission, and that is only the laser. And then the main one for the triplet states is kinetic absorption, and that is both lamps. They're both controlled by the software. So, kinetic emission, you have setup, multiple, and map. Setup, you have a new sample, and you just want to check what is the best experimental condition for your sample. So, setup just repeats each measurement. No accumulation, no averaging. You can change the wavelength, the oscilloscope settings until you have a good sample. Multiple is after setup, multiple will allow you to do the averaging, which will improve the quality of the signal to noise ratio. And finally, you have the wavelength map, which allows you to make measurements at different wavelengths, and at the end, you can create a spectrum from the data. Okay, so setup. So, three tabs. The first one is the controller. Normal operation will be laser timed, laser shutter timed. Then the monochromator wavelength. Now, your sample, all samples will be different. For my sample, I'm going to look at the fluorescence or luminescence at 610 nanometers. Bandwidth, it helps to determine how intense the sample will be. Just the amount of light reaching the sample. For the fluorescence, you can make that quite wide. For the transient absorption, you have to be a little more careful, and I will explain that later. Secondly, you have the control of this oscilloscope. So the two main things are how long you want to measure your sample for and how intense your sample is. So for your sample, you will choose which is most appropriate. And finally, backgrounds. This is just for noise. This is just to improve the quality of your sample. So noise background, you can have none. Zero baseline, just make sure that there's nothing before the sample. Laser noise, if the laser is being very noisy or your emission or transient absorption is very, very weak, you can do laser noise, and again it can improve the quality of the signal a little bit. So, what I'm going to do, just check all these. Take this to 400. What I usually recommend is when you start a new sample you have not used before, try 4,000 nanoseconds, 400 millivolt. That's the starting point. So, I'll start. Okay. So, you're seeing a signal. Normally, if the laser was working properly, this would be quite a lot larger, but this is what we have to work with. So, you can see it's very small, so maybe I will make this 5 nanometers. Oops, 5. Okay, so now we have a larger signal, it's getting better. Still quite small vertically, so maybe I can change the vertical scale. Okay, so the signal is not actually larger now, it's just that the oscilloscope is being more sensitive. Okay, so that looks quite good. Right. So if your sample, if you do not see the whole decay in your sample, you can go to a longer time scale, for example 20 microseconds. So you can see it squashes it all up. So this is just to help you for your particular sample. For my sample, the 4000 nanoseconds is a good setting. Right, so now I'm quite happy with that measurement, that looks quite good. So, I want to improve it a little bit. I go to multiple. What we'd do here is maybe averages, maybe do 5 averages. Everything else, by the way, is all carries over from the setup measurement, it's all the same. So do 5 averages. Okay, not too bad. Let's see a little bit of maybe laser noise. Let me just repeat that. We'll do the laser noise, see if it looks any better. Takes a little longer doing this. Do it this way. Okay, right, so that's a nice measurement. So what I'll do now, I'll save it. So we'll save as. Twenty.
20.
So this is ruthenium bipyridine, usually called laser-induced fluorescence at 610 nanometers. Okay, so I have my data. So 2 days' time, you want to come in and know, what did I do with my data 2 days ago? So, file, open, PC, training, so WP, so we have the data, and along with the data, it is properties. So, along with the actual data, a lot of the experimental information is saved. So this is your laser, what your laser was doing. And the probe, we're not using the probe at the moment, we will do shortly. Software version, here, I want to show you 5 averages, total of 5 averages, 610 nanometers, 5 nanometer bandwidth, and you used 160 millivolt vertical scale and 4000 nanoseconds horizontal scale. So if you cannot remember what you did previously, you can look at this and remember all your experimental conditions. Okay. Now, if you want to save in ASCII, this is done automatically. Test results. Right, so there's 2 files saved here. This is what's called the binary file, and that's what I've just shown you. You also have a text file, so if you want to export this to another computer, it is already in ASCII format. So the other thing you can do now, you can measure your decay time. So you do data, exponential fit, tail fit. To start the algorithm, you just guess, maybe 100 nanoseconds. And apply. Okay. And that's, say it's now 376 nanoseconds. So here, you have a nice decay. Residuals are very flat. That's pretty good. Now, I don't know if anyone is familiar with fluorescence systems, but in fluorescence you have this measure called chi-squared, which is not particularly relevant here, so do not worry about this value. In fluorescence, if this was a fluorescence decay, chi-square should be between 1 and 1.3, but for transient absorption, with this, because we use the oscilloscope, the Poissonian statistics used in fluorescence are not valid, so do not worry about the chi-squared, just look at the goodness of fit and the residuals. These should be nice and random, as you can see here. If you see a pattern going like that, try doing a second lifetime. Okay. Now the other thing we can do, we can make a spectrum. So, wavelength map. Right, so here, now I'll start at, it's 532, I'll start at 560 nanometers. Then we go to 700 nanometers. 10 nanometer step. Okay, bandwidth, so far I've been using 5 nanometers, so I will still use 5 nanometers. Step size, I'm going to do 10 nanometer step just to be quick. For good quality, 2 nanometer or 5 nanometer step will give you better spectra. And I'll maybe just do 3 averages. This tells me down here how many measurements I am doing, 45. Especially with the transient absorption, you can find yourself very quickly getting into several hundred measurements, and you have to be aware that this will take you a long time. So 45 is okay, that's going to be about 1.5 minutes.
Year on the entity.
So what happens at the end here? You see, no, sorry, I'm thinking of transient absorption measurements. So there you have your spectrum. So I'll save it. Save it as LF. Right, so what you do with this, there is a button here, cursor on. So you move the cursor to just to the start of the measurement. Right click your mouse and press this set time 0. So here it just adjusts the time so that 0 time is now when your decay begins. And then you do data slicing, and I'll start at 0 and maybe run to 1000 nanoseconds. I do 5 slices. This is all just what you feel like, so I'll do that. As you see the spectrum, so it's quite a simple spectrum, maximum about 610. And because each one is 100 nanoseconds long, you gradually see the spectrum decaying. That's what you do with the spectrum. So, the transient absorption measurements. So, set up multiple and map as before. What you have this time is you have 2 extra boxes here, probe and probe shutter. So probe is normally pulsed unless you're measuring something very long, like 20 milliseconds, because the pulse can't last as long as that. And the probe shutter is timed, so it opens so that you do not bleach, the UV light does not bleach the sample. In this case, for my sample, I'm going to measure at 370 nanometers. Your samples will be different. Oscilloscope, start at 4,400. I'll probably do the laser noise. We'll see. So let me see if I'm going to see anything. Right. So what we have here is the probe light. So the probe light is shining through the sample, and at this point the laser hits the sample. So the sample goes into an excited state, absorbs more of the probe light, and then gradually relaxes back to the ground state. And that's basically what you're measuring for the transient absorption. The triplet state. This is the triplet state decay. Right. So a couple of things you have to be careful with. I did not make the slit size as wide here. I left it at 2 nanometers because the maximum signal size is 650 millivolts. If you go above that, the PMT can start to saturate and become non-linear. So always make sure your signal is smaller than 650 millivolts on it. It's scaled here 6.5 times 10 to the minus 1. I can maybe do a little bit more, maybe 2.5 and might be okay. That's as far as I would want to go. What I will do, I'm going to make this 160 millivolts. Let's make the oscilloscope a little more sensitive. 2.5 is getting too much. Yeah, if it goes above 750 millivolts, you will get to see the signal too large. So put that back down to 2. Okay. So as before, you now have the signal that you want to see. And now this part multiple. We do 5 averages. Start. what this does, so this is your measurement. So this is the same as the oscilloscope, but this is measured in voltage. For the transient absorption, you really want to convert to a scaling that is representative of the sample. So normal one used in transient absorption is called delta OD. And it's also, the delta OD is the same as the change in absorption. So it's the same thing. We tend to use delta OD. So what it does, it measures this and then calculates the delta OD at the end. So what I always recommend, if you're saving it, save the raw data, because here you have this voltage information that is lost in the delta OD. So just save that first. And I'll just show you how the delta OD calculation is made. So data, delta OD calculation. So this is the formula that was used. So I naught is this value, the average, maybe the first 5% of the average. And then IT is your time, and just it's a logarithmic measurement. So that is the conversion from here to here. That is what is done. Right. So, as before, data, exponential fit, tail fit. Again, guess value. Nice flat line. Now, by coincidence, for this particular sample, the fluorescence and the transient absorption are very similar times. That is not normal. Usually the fluorescence is much faster than the transient absorption. Right. So, there are some other factors you have to consider when you're making the transient absorption. This time scale is quite easy. When you get to 100 microseconds, maybe a little bit more, then it becomes a little more difficult. So, I'll show you what I mean. I'm going to go to a very long time scale just to show you the profile of the probe beam. This is not a measurement you would make, it's just to show you. So what happens here, with this, at the very beginning the shutter is closed, and then at this point the shutter opens, and the shutter is fully open, so this is the steady state probe beam. And then the pulsar hits the beam, and you can see there's a large increase in the light output, and then it goes along through this phase. This is the pulsed light, and then the pulsing stops after 6 milliseconds. The light level drops, and then just at the end here the shutter will start to close. So what you're measuring is somewhere on here. And what you can see also in the millisecond time scale, it's not flat. So we have to do a compensation measurement to stop for the flatness. So I'll go back to normal settings. And I'll do just to maybe 1 millisecond. Again, for this particular sample, this is not a sensible time, but it's to demonstrate the probe background. So, go to multiple, go to backgrounds, and you can see, as well as the noise background from before, there's a probe background. I'll do that one. Just the offset. Go back to setup. let it run for 2 or 3 measurements. The software will automatically look for the probe light. Okay, here we are. Stop. Incidentally, that little spike is what we were looking at earlier. That's the transient absorption. So if I do multiple, no probe light, sorry, no probe correction. Okay, so you see this is quite a large, very not flat. So we're doing a probe correction. So now you see this has become flat. So if you're measuring on this time scale 1 millisecond, then you do this probe correction. And it makes the measurements better. Now, the other one you see here called fluorescence correction. It is possible with the transient absorption measurements that your sample will both fluoresce and show transient absorption at the same wavelength. So the fluorescence will make the light signal larger, transient absorption smaller, so they cancel each other out. You cannot see the proper transient absorption. So the way to correct for this is to measure the fluorescence explicitly. So now we'll go to 610 nanometers. I think this will probably say signal too large. So, if I measure this with 5 averages, no corrections, so what you're seeing here looks like a very weak fluorescence, which it is. But it's a combination of the fluorescence and the transient absorption. So it's not the true fluorescence. The true fluorescence you can measure just making a fluorescence measurement. But to get to the transient absorption, what you have to do is fluorescence background. Start. You're measuring the whole signal here, and at the bottom you can see this is the fluorescence. Okay, so you see the delta OD goes positive, so there's a weak transient absorption here, which the fluorescence was hiding. So that's. You can always check if your sample has fluorescence, you have to do this correction. If there's no fluorescence, then there's no need to do the fluorescence correction. Right, last measurement is the transient absorption map. So this one is quite difficult, or it can be. The main reason is the probe beam changes intensity as you change wavelength. So you have to be careful that you do not go to somewhere that is going to be too intense. So I'm going to just test at 500 nanometers, because that's where the probe light is quite intense. Start. Okay, so you're already telling me the signal's too large. Safer, it's 5.530 millivolts, that's safer. Right. So, that's first tested done. The second test is that because the software tracks the intensity of the probe beam, I need to go to my first level to start at 312 nanometers. Oh, now I need to think about this. No, I don't want to do that, it's going to be 532. Start it. Yeah, I'm used to work 355 laser. This is 532 laser. So just let this run until it finds the beam. Okay, so that's the intensity. Now I'm going to do a couple of other things here. I'm just going to oscilloscope take this up to 400 millivolts. And the other thing, I'm going to run the laser a bit faster. So I go here to laser. So far I've been running this single 1 Hertz. I'm going to change to 5 Hertz. So it's basically your system frequency is going to be 5. The other parameters here depend on your laser, so you will not change them unless you change the laser. Right. So, I say I'm going to go to mode 2. Okay. Right. So, I'll just do a setup so you can hear what it sounds like. Now you're ready to start the mark measurement. Start at 320. Stop at 700. Step 10. 1.3, same as this one. And step 5. Right. Rubber duty water. So what you're seeing here, this is the probe light intensity increasing wavelength. Oh. Yeah. Hold on. Sometimes when you stop and start the laser, the shutter closes. So, open the shutter again. So, I'll start again. There's no laser. These map measurements, they're quite long lasting, so this is going to be another 2 or 3 minutes. Okay. So again, you can save the raw data file. So what we do now, final bit, it's same as before for fluorescence. Cursor on, set time 0, and do the data slicing. 0 to 1000. Okay, because it's a small signal, it's a bit messy, so I can smooth it a little bit, do a 3-point smooth. Right, so This is the transient absorption when we're looking at it 370. Here's a little bit of fluorescence, net fluorescence, which if I did the fluorescence correction, this would be flatter. And what we have here is a photo bleaching. Basically, this sample is most absorbent at 450 nanometers. So the 450 nanometer light, most of the excitation site has already been done by the probe, so there's very little for the laser to do, and it ends up that the probe light actually finds it slightly easier to shine through at this wavelength, so the light level increases. The photo bleaching is always related to the transient absorption, unlike the fluorescence. So you're likely to see bands like this. To tell the difference between photo bleaching and fluorescence, make a fluorescence measurement. If the signal is still there, it's fluorescence. If it has disappeared, it is photo bleaching. Right, so that's the basic operation of the system. Right. So what you do now is you get a sample. Maybe your professor has a sample, and you can do that tomorrow morning.
Yeah, they did.
Yeah. Oh, okay, oh, there's one here.
आपके पास रहेगा तो आप भी ला सकते हैं फ्लोरेसेंस की वजह